Finally, let's wrap up section 2 by looking at a couple of series that we can find out not only they converge or not, but we can also find their sum. That's kind of rewarding in a weird way. The first one, by far the more important of the two, is the geometric series. And you might be familiar with this. I notice I haven't given myself some room here to work, so I'm going to come down to the bottom of this page if I can find it. There we are. And I'm going to goof around with the geometric series. So geometric series, and we've seen it before actually in an earlier lecture. They're the ones that if you took, like, let's remember how it went. It went 12 minus 6 plus 3 minus 3 over 2 plus. What I'm doing is reminding you, do you remember this guy from a previous, when we were looking at sequences? Yeah, this guy, what's happening every time we jump, let's put that in another color. Every time we jump, we are multiplying by the same number over and over again, and that number is negative 1/2. What do you think about that? You're multiplying by negative 1/2 each time. Okay, so times this, times negative 1/2 again, times etc. Okay, that's an example of a geometric series. They typically look, now, I think you might find this in your notes. We had a formula for that. It was like 12 times minus 1/2 to the n minus 1. But in this case, we're actually adding it up. So n is equal to, 1 to infinity. And that's what it looks like if it's written in sigma notation. We get a feel for it jumping from term to term to term. We are multiplying by the same number over and over again. And that's what it looks like. I can invent another one, series, for instance, n is equal to, I'm tired of 1. How about we start at 0 to infinity, and we decide to go something like, I don't know, 4/3 to the n, and that's it. Well, in that case, when n is 0, we start with 1, because it's the 0 power, but then we have 4/3, and then we have 16/9, and then we have etc. You see, it's got that idea of jumping by multiplying by 4/3 each time. And you notice when it's written as sigma notation, you guys, it looks like an exponential function oftentimes. We got some good examples here. This might take a little bit of time, but it's worth it. Anyway, the development of this guy, I'll do this very quickly, would be a typical series, and I don't care where it starts, is A1, okay, we'll say r to the n minus 1. So we'll start it at n is equal to 1 to infinity. This guy is A1, there's a reason I called him that, and then A1 times r, and then A1 times r squared plus etc. Okay? If you want to argue this with partial sums, which is what they often do, they go, the nth partial sum is the first all the way through the nth. A1r plus A1r squared plus ... plus out here is like A1r to the n minus 2, and then the very last one maybe is A1r to the n minus 1. The next trick is to write underneath it the same thing but multiplied by r. So you do that and you go, okay, that's A1r plus A1r squared plus A1r cubed plus ... plus. If you add another factor of r here, you get r to the n minus 1, and then out here, A1r to the n. And then in textbooks, they say subtract. Subtract these guys. Because if you do that, on the left-hand side, you have Sn minus Rs sub n, which are the partial sums. And on this side, look what happens. The survivor, we have one survivor, this guy, A1, but then the rest of them, when you subtract, cancel out, cancel out, cancel out, cancel out, cancel out. And look, we have another survivor here. So it would be minus A1r to the n. Have you seen this before? You might be going, oh yeah, I've seen this before, maybe. Okay, we're not done, because next you factor out S sub n, and you're left with 1 minus r. And I'm going to factor out A1, why not? 1 minus r to the n. Let's see how much paper we got left. Not much. So that means we've got a formula that says S sub n is equal to 1 minus r, okay, Weber, come on. a1, 1 minus r to the n over 1 minus r. Now here's the thing. If absolute r is less than 1, then r to the n goes to 0 as n goes to infinity. I'm doing it real quick. This is better as a classroom discussion. I'm explaining to you the following fact. It says this: series a1 r to the n minus 1, n is like 1 to infinity, converge to a formula, a1 over 1 minus r, because this guy, if r is small enough, goes to 0. See that? If absolute r is less than 1. But diverges otherwise. Okay? I think I've discussed this before in another class, and I kind of wish I had the notes here to see that. But this is really quick to give you this formula. What's important? Well, what's important is this guy. A lot of people are probably rolling their eyes on this particular lesson, but that's how you develop it. If r is small, like if r is like 2/3, you take the next power, r squared, it's 4/9. You know what? That's actually smaller than 2/3. This is less than a half right here. This is greater than a half. What if you take r cubed? Well, you got, okay, 2 times 2 times 2, you get 8 over 27. It's shrinking. I'm shrinking. It goes to 0. Okay? So let's go do these problems up here in a similar manner. Oh my gosh, I've got too many of them. I might have to pick and choose. This might take us a while. Okay, so the first one, and I might just do, I don't know if I'm going to do all of these guys. I might start some of them, but here's how you do this one from start to finish right here. You go, okay, this particular guy looks like, you see the exponentials? It looks like it's geometric. All of them, except for this guy, what the heck is that? All of them kind of do. But what does that mean? What do I do with that information? What I do is I write terms out, man. I go n is equal to 1. I've got 3 squared over minus 2. N is equal to 2. I have 3 cubed over 4. N is equal to 3. I've got minus, what is that? 3 to the 4th over 8. So what's happening is, if you notice, is we are jumping this way by a factor of times, what is it? Negative 3 over 2. And again, times negative 3 over 2. Okay, so typically I tell people, the first guy is a1 always. a1 is the first term. In this case, negative 9 over 2. The r is the jump that we just discovered is negative 3 over 2. What do you think about the divergence convergence of this series? Well, absolute r is absolute negative 3 over 2 is equal to 3 over 2. And you know what? He's greater than 1. He's not less than 1. You know what you're allowed to do right now? This implies it diverges. The multiplier's too big. He's bigger than 1. We got to stop. Okay. Let's go to the next one. All right, in this case, if I write, you notice it's almost the same thing. So I'm thinking it's geometric. I'll write it out. It's going to be a negative, if n is, you're going to get a negative 9 over 8. Next one, though, is a positive, 27 over, oh boy, he's big, 64, negative. And what you're noticing is the first term, of course, a1, is negative 9 over 8. But your multiplier r, this time, when you jump from here to here, you multiply upstairs by 3, downstairs by 8. You can see it in the formula. So you go, okay, it must be the multiplier is negative, 3 over 8. But you know what? Absolute r is equal to 3 over 8. And this time it's less than 1. That means it converges because r is small. He'll go to 0. Not only that, but the sum itself, up here I'd say something like, basically, what is the sum? You go, well, the sum is the following. It's a1 over 1 minus r. a1, and what we took the trouble to spell out, is negative 9 over 8. And downstairs is 1 minus, r is a minus 3 over 8. So we're getting negative 9 over 8 divided by 1 plus, so that's going to be, I think it's 11 over 8, isn't it? Right? And so therefore, negative 9 over 8 times 8 over 11, and we get negative 9/11. The actual sum at infinity, going all the way out there. If you let this thing go and go and go and go, the sequence of partial sums, that is S1, S2, S3, they are converging, and this one we can actually tell you what the sum is. It's negative 9 over 11 by using that crazy formula that we devised at the bottom of the page. You're going to have to slow it down maybe and watch this a little more closely. I'll give you some pointers on the other two. I'm not going to do them for sake of time. I'll let you kind of, you're going to work for me? Okay. I think it's freaking out on me now. In this case, we use a property of series that I didn't discuss, and we can actually split this apart. N is 1 to infinity. People have trouble with this. 3 to the n plus 1 over 5 to the n minus 2 to the n over 5 to the n. You know what happens? Because you're adding terms together, you can split this apart and jumble all the first terms together into one series. And over here it'd be 3 to the n plus 1 over 5 to the n, but then minus another series. Can you do that? Can you do it with integrals? You can do it here too. Okay, so this is another series, 2 to the n over 5 to the n. It's cute. What you can now do is come up with, there's going to be an a1 over 1 minus r for that guy, minus another different a1 over 1 minus r for that guy, and get your actual sum. See, the multiplier I can see here is 3 over 5. Let me point that out to you. This multiplier here is 3 over 5, but if you go this way, it's 2 over 5. Both those numbers are less than 1. I know it's a little advanced what I'm saying to you, but that's how that works. You might want to try it. Maybe we come back or when we review, or any questions you have in class. And this last one is cute. You go, this is 2.3 plus 2.3 times 0.01. In other words, here's this piece, and now here's this piece. In fact, I'll do it in stages. I'm sorry about that. I'm worrying about time on this one too. This is 2.3 plus 0.023 plus 0.00023 plus, it's geometric. It's 2.3 plus 2.3 times 0.01 plus 2.3 times 0.01 squared plus, and you can treat that guy as an a1 over 1 minus r and get an answer for that too. So I kind of ran through those. That takes too much time on this video. It might be worth it to do it, but it really prolongs the battle. So some of that I'm going to leave to you, but I did give you a good start on that. This is a long video. We're going to wrap it up. This section is a lot of information about series. This is about telescoping series. Typically, I might put one on the test. They're not that interesting to me, but I'll show you how to do them. Okay. Series whose terms cancel each other out. So what I will do is I'll take a look at this one, maybe get this one started, and we'll stop this particular video. Okay. If you plug into this thing, it's kind of a bummer. You get 1 over 1 times 1 plus 1 plus 1 over 1 times 2 plus 1 plus etc. And what you're getting is 1 times 2. You're going to get a 1/2. This is 1. Okay. Oh, this would have been a 2, huh? So 2 times 3 is 1/6 plus. And does it converge or diverge? I couldn't tell you. I don't know. But I do it this way, though. Watch this. You're not going to like it. Series, maybe you will. 1 to infinity. 1 over n plus 1 is equal to series, big old bracket, a over n plus b over n plus 1. Are you kidding me? No, I'm not. Partial fraction decomposition. That's what we do. I'm going to do it right now. So we've got like this guy up here. If we clear fractions, you've done this before. It's been a while. Looks like that. And if n is -1, you get 1 is equal to b times -1. So you get b is -1. Likewise, n is equal to 0, you get a is equal to 1. So what? So look, watch this. This is crazy. You get series, n is 1 to infinity, bracket. What do we get? We got a is 1. So 1 over n minus 1 over n plus 1. Okay, so what? So it looks like this. When n is 1, you get 1 over 1 minus 1 over 2. Plus, when n is 2, 1 over 2 minus 1 over 3. Plus, when n is 3, 1 over 3 minus 1 over 4. Plus, and it keeps going. If you really, really, really wanted to make this scientific or mathematical, you would just go, when n is equal to n minus 1, you get 1 over n minus 1 plus 1 over n. That's right, I plugged n minus 1 in right there. And then finally, plus the last one, the nth term. So you could say this is s sub n maybe, and you can go, this is 1 over n minus 1 over n plus 1. Okay? Now, I used to say I want you to write that out and all that stuff, because look what happens. Did you notice? Cancel. Cancel. It's telescoping, like a telescope smushes in, like a pirate telescope. Think of what's-his-face, Johnny Depp or whatever, and his crazy telescope. And all these guys are canceling except for the first and the last. Okay? So S sub n is 1 minus 1 over n plus 1. And as n goes to infinity, comma, S sub n goes to 1 minus 1 over infinity, which is 1 minus 0, which is just 1. That means the infinite sum is just 1. This guy right here that I'm circling up here, if you were to add a bunch of come up with a bunch of partial sums, you would end up, they would go towards 1. Okay, I'm going to leave this one for you, but what you would have to do on this one is you go, all right, that's the same thing as series 2 over factoring n plus 1, n plus 3. And then what you would want to do is break it apart. How about a over n plus 1 plus b over n plus 3. It's a little bit different because it leapfrogs when they cancel a little bit, but that's how you handle telescoping series. And I think that's it. That's a lot of information coming at you in this section as well. And that's at least a start for you guys as I turn this thing off. I'll see you on the next video.